All right, welcome back to System Software, everybody. We're coming to the end of our section on files. And so just a couple of reminders. The video and the board from last time is up. I also re-recorded the file basics, the course from a week ago, or the lecture from a week ago that I failed to record it. My recorder crashed. So re-recording that is up. Our questions from last time. Questions on projects. I think we have the Hello project due tonight. Yeah. What's the error? And also put it on EdSTEM as well. So I may not have caught every possible error. So it definitely doesn't say hello is up to date, I'm guessing.
It doesn't say hello is up to date. It says that there's nothing to do for all.
There's nothing to do for all? Yeah, that means, I think the version I got the output from is different because that's an okay output. I think that must be the Eustace. I must have got it from my local machine instead of Eustace. I'm guessing that's what happened. So that's fine. Yeah, if there's nothing, that should be fine. Put it on EdSTEM and I'll rerun it on Eustace and get the right error, the right correct message. So I think this is probably what I had on my local machine, looking at the call to make. All right, other questions on anything from last time? Homework project? Excuse me. All right, let's go over the homework from last time. So remember, the homework is not graded for 100% accuracy. It's graded for genuine effort. So let me know if you're getting a 0 and you don't think you should have gotten a 0. If you just make an attempt at the homework, you have something reasonable, you're actually responding to the question, you should just get full credit for the homework. They're not meant to kill your grade. They're meant to just make sure you're keeping up. There'll be the midterm exam questions. There's basically from suggestion from students in the past who wanted like kind of concept questions or other additional questions to help remind them of what to take away from lectures. And I also don't want them to like kill your grade. So I will throw you some curveballs in these or make you kind of have to do some work or thinking or banging your head a little bit. All right, so first one, write a snippet of C code using a system call as described in class and in the readings that opens a file hello.c for reading. Questions on this? How to do this one. So, not that one. Let's get to the notes. So just as a reminder, the whatever is in the slides plus my presenter notes are all linked here on the topic name. So this is literally just the slides in outline format. Okay, so we saw that in class last time. I'm pretty sure I did this last time. This is, well, let's use p-error. This is how you open a file for reading only with a syscall. And you could instead use hello.c here, the string. Questions on this one? Questions on this homework question? Yeah.
I didn't know that we had to put the error call for the snippet of C code that opened it. Is that still fine?
You're not going to lose points or anything. Okay. But when doing systems programming, you should do that. And I think I specify this explicitly in tonight's homework. So it's okay. It's okay if you didn't do that for the homework. That's okay. I really just wanted to remind you of the open syscall and its inputs and outputs. Yeah. Where do you see X? See what? No. Not necessarily. Exit failure, actually, I think is a macro that is just one. So it's, yeah. There are conventions, I don't think I linked them, but there are conventions, if you look in like the Unix documentation about the error code numbering, and this will end up being one. So yeah, as long as you indicate to the user that it's like an error, but this is kind of application dependent, what exit code you'll use. We'll see that more when we look at I'll use those in today's project, the file system project. I'll give you the error codes that you should use. But generally, Unix applications use these to communicate different error states to the user. So for instance, let's see. Okay, cat doesn't document it. grep is a tool that does search. So you can if you look in the documentation, these tools will have this exit status section. So exit status 0 or exit success is another keyword, a macro. That means nothing went wrong. That means no error. It's kind of the opposite of like C's conditionals. So C conditionals, non-zero means true. Here, this is different. This is not Boolean or a Boolean value. This is an exit status. Exit status 0 means okay, and then 1 or above is an error. And it's application dependent what these errors mean. There's some like sort of conventionally reserved ones, like 1 is usually used for general errors. In this case, it's used in this case. But it's to communicate what went wrong to the user of the application. And I'll have you, I'll define what these should be for your program that you'll write for the FS program. But that's a good question, yeah. What should go here? And it's really, there are conventions, but it's application defined. Other questions on writing the system call? Yeah. No, it's by snippet I mean a fragment of code, a subsection of a complete program. Yeah, so that's fine. That's fine. So yeah, I'll have questions like this on the exam. So it's good to kind of get that language out of the way. But yeah, that's what I mean by a snippet. Other questions on question 1? Yeah. That's right. Yeah. And for all of these, and especially the ones where you may not have seen the answer explicitly in class, I was sort of hoping you'd look at the man page for open. And if you ever forget what the arguments are, or what the order is, or what the types are, this documents it for you and tells you, so you can see, it tells you the type here. It's a character array. And it tells you what the inputs are. So it opens the file specified by path name. And there's just a question going back to, oh, yeah, sorry, go ahead.
When I do man open, it gives me CD open manual entry.
That's right. Why is that? So the reason is there are multiple like volumes of this, they're called sections of the man page, and each of these may have the same similarly named commands. So by default, man pages just kind of give you the first one. So if I do man open, yeah, I get xdg open. This number here after the command is the section of the manual page that you're looking at. So that's why in the slides and in the notes I put man 2 open. So it's telling the man page that I only want to look in the second section of the manual where the syscalls are defined. You could also do man A if you're just not sure which section it's in. Man-A will look at all the sections one at a time. So when you quit, it'll prompt you, and you can hit enter to look at all the other versions of open. Yeah. It'll definitely work on Eustace. Your own system, it depends on whether you have a Unix-like system installed. So in Windows, you can get that with Windows Subsystem for Linux. Like you download the Ubuntu application. Git Bash might have it as well. I'm not sure. And I think Mac OS should have it as well. Do the Mac users, do you have the man pages? I think you should, because it's a BSD Unix. It's a different implementation of a Unix kernel, but it is uses a lot of the same tools as a Linux distribution. Okay, so this one, I don't think I explicitly did this in class yet. Did I get to this? Yeah, I didn't cover this in class yet, so this is one where you have to look up in the man page. Did anyone figure this out, or maybe Google it or something? Yeah, so what do you have to pass to the system call, to this system call, to tell the kernel to create a file? Yeah. What is it? Oh, create. So there's this. And if you didn't find this, that's okay. You're not going to lose points for missing this. And you would have had to Google it or read through the man page. The open command takes the path, and it takes flags, and it takes a mode. This is the permissions, the file permissions mode by default, optionally. The flags are described down here. So there's the full list of file creation flags. And yeah, if you didn't just read this whole manual, you may not have found it. But there is a flag that you pass called create, or create, that will, if the file doesn't exist, it'll create it for you. So this is how kind of low level your programming you're doing. That if you ask to open a file, the kernel will just say, that file doesn't exist, I'm going to error out. You have to manage that, or tell me, the kernel, what to do in that situation. And so if the file doesn't exist, you have to, if you don't want to get an error, a file not found error, you can tell the kernel, hey, I'd like you to create the file if it doesn't exist. So that's what the create flag does. Or that's how you can get the kernel to do this behavior, use the create flag. Questions on that? That's just a knowledge thing, but it's documented in the man page. Yeah? Yeah, so if the file, if the file exists, it doesn't. We'll get to that today as well when we look at the file system project. It won't necessarily overwrite it. It depends on whether you're opening it for reading and writing. If we're opening for reading, then it's not gonna overwrite anything. If it's open for writing, it won't overwrite until you start actually writing to the file. I think you've used fopen and fwrite. Have you used fopen and fwrite? And what's the behavior there? So if you open the file for writing. And if it exists, it'll just overwrite it, right? If you just start writing to it. So it's the same behavior here. It'll open. You've told the system, I want to open this for writing. It's not gonna provide any protections beyond what you asked it to do. So you'll just start writing the file and overwriting it. There is an append flag as well. So you could tell the kernel to open it and move the file pointer to the end of the file, so that when you're writing, you're appending instead of overwriting it. So the kernel designers also thought of this situation as well. So definitely don't expect you to know all these. I don't know all these or use all these. I'll give you the flags to use for the project. Yeah.
You know what happened to the E?
Say again?
You know what happened to the E in Create?
Yeah, I don't know. Maybe they were. I'm not sure. This might be something for Stack Overflow or something. I think maybe they had 5 character limitations or something.
That looks like it. Yeah, I guess the other one.
Because there's a system call called create as well. You can just explicitly create a file as well. Oh, it's part of the open documentation.
Maybe they didn't know how to stuff.
They didn't what?
They didn't know how to stuff.
I doubt that. That one I doubt. It probably was a character. They wanted to have some character limitation. So this call was added later. It almost looks like it's supposed to be open at create.
Well, if open at is so cool, then why is there no open at 2?
There is an open at 2.
Okay, well, if open at 2 is so cool, then why is there no open at 2 too?
Yeah, I don't know. I mean, maybe this is create at as well. I really don't know. I think there was a character limitation. This was done in the 60s. So this is something to Google. Ask on EdSTEM. We can find some documentation of this. But this has become a standard. This has become the POSIX standard that I think even Windows has. You can see this is a POSIX standard. or the open-at is. But I think creat is a standard now. All right, last one. So what might it mean if the error code says no ent? File path has been created. Okay, so I don't remember what it is, so I'm going to look it up here. So also, if you remember, we talked about error handling. How do you handle errors? Oh, I also looked. There's a good. There was also Stack Overflow discussion on the history of using a separate error state, which ask on stem. I can send it out or just Google it. Basically dividing the return values from the actual return value of the syscall with these error state. So there's some long discussion on why the error state is separate. But if you remember, in our Unix standard, the syscall error handling happens by checking for a special return value that indicates an error, and then looking at the error no, looking at this error number variable, also 5 digits, 5 characters. And also in the documentation, you'll see a section under errors that'll tell you exactly what each of these errors that the kernel returns means. And here there are 3 situations where ent could happen. So it could be if the file doesn't exist and you didn't tell it to create a file. It could be that you gave it a path, but a component of that path, one of the directories, didn't exist, etc. But anyway, I just wanted to test your kind of if you remember to look up in the man page. That's where you can find this documentation of this stuff. Questions on the homework? Yeah. The second question. Oh, I didn't do the second question. Sorry, this was testing the file. So okay. If we're opening a file called hello.c and the current working directory is /temp/ what's the absolute path of the file we're opening? Any takers of what? So we have the file, relative file hello.path, and the working directory /temp. The full absolute path is just concatenating the two, or joining the two paths with a path separator. So that's the full path. All right, any other questions on homework 6? Questions from last time? Questions on the Hello project? Yeah, which one?
Yeah, the man page for the error number, just so I can see it in the lecture recording.
Yeah.
Thank you, I appreciate it.
Yeah, I mean, it should be there. I was recording the beginning as well.
Oh, okay, I didn't know
Yeah,
that.
the beginning's recorded. You mean how I got to see the error codes?
Yeah.
Yeah, so I just did man to open. And then you can just scroll down with arrow keys or page down or space or use the Vim numbers. You can search in this mode with / and then capital error, hit enter, and then we've got the error section.
Perfect, thank you.
No problem. Okay. Okay, let me continue going into syscalls. So last time, just a quick refresher, we did this in the homework. This is the template for making syscalls. Most of the time, you'll just exit out. But there are, I can't remember if I forced you to have any cases. I think I put it in bonus projects. There are times when you want to handle this error gracefully, or where you want to allow for different situations. Like, for instance, the copy command, by default right now, will overwrite the file, but it won't overwrite a directory that's not empty. You could change that behavior. You could write your own version where it will overwrite the directory. And in that case, you'd have to test first whether the file exists. Maybe you open it, it fails to open, and then you do something different. But most of the time in this class, unless I tell you in the project, this is the standard error handling we're going to do. We're just going to give up and quit. And so for all syscalls, you have the name of the syscall. It's a function call. The inputs are defined by, you'll see the definition in the man page. The meaning of the inputs and the outputs are defined by the man page. Sometimes inputs or outputs are also given as arguments, which is a C thing. C only has single return values in C, but you can overcome that by passing pointers in or values by reference. And then we check whatever the error return value, the erroneous return value of the syscall is. It's not always -1. It might be 0. Where do we find that information about the return value? In the man page. The man page says, or in the Linux programming interface textbook. So this tells you what the error return value will be. All right, so let's take a look at, and this is the example program. I went over this last time. Any questions about this C program? The arguments, we think we went over arguments. This is the call we just talked about. Files will be closed when the process ends, but it's good practice to call close. Questions on this from last time? Yeah.
What could cause an error in closing?
I mean, the kernel, so one of the big errors that the kernel can have is it can be interrupted by some other process or some other interrupt, and that can prevent the close from happening. It's true for all system calls. So actually, you can see in the documentation, just like for open, these are the possible error states. These are the possible things that can cause it to go out. So, I/O error. I don't know. That would be bad. I don't know if that could happen. Maybe somebody like pulls out the hard drive or something. And then there are these kind of asynchronous signals that could be passed through processes. Take an OS class. They'll talk about just like inter-process communication stuff. But also, yeah, you could also just try to close a file that's not open. That's another case. Excuse me. Okay. Any questions? Yeah.
I can tell you from personal experience that a lot of programs are not well equipped to handle the hard drive being disconnected. I know
Yeah.
because my old hard drive on my computer loved to just randomly disconnect, and it was very fun.
There you go. Now, as an application writer, you could gracefully handle that kind of stuff.
Yeah, I didn't even consider it, and I got all sorts of fun errors.
Yeah, I mean, it's kind of a safe assumption. I mean, you probably can't continue the application anyway, right? Like, if you're writing a Word doc or something. But I don't know, maybe actually you probably could. You could hold it in memory or something. But yeah, so yeah, this is kind of the common choice is to, yeah, and this is in all computing. Remember we talked about what bugs are. Bugs are when the machine does something different from what we expect. The machine is not necessarily wrong. Yeah. Oh, I forgot to write these error cases. So in this case, you would open the file, and then there would be an error, so it wouldn't actually open it. And the file descriptor would be -1. So the program would just move on with those values. It would be like if you accidentally set a null pointer and didn't check it, and then went on to dereference it later in the program, the the manifestation of the error may appear later in the program, but the actual bug, the thing that you were not supposed to do, may appear earlier. This is kind of the problem with tracing bugs. But the program will just continue running, and this close will get -1 as a file descriptor. That's not a valid file descriptor. So then close will fail. But if you don't check that error, the program will just terminate. So if you were doing things like trying to write to a file, you just have a silent failure. You would think the file is being created or written to, but it's not. And this is another good lesson for why you should just like do error handling. Consider the inputs that consider all possible inputs, even the ones you don't think apply to the thing you're solving. And whenever you have, in this case, whenever you have an error, you got to check the error. But if you're testing things with an if statement, consider what the else should be, even if it's I just quit the program, because explicitly giving an output for the error is better than letting some unexpected behavior happen later in the program. So I think this is good practice, even though you may not do systems programming. Most of you probably won't do this kind of Unix systems programming. It kind of forces you or teaches you how to do this error handling at a very fine grade level, so that when you have these easier high level languages where the error handling for basic OS stuff is done for you, but not for the application you're trying to do. For the application you're trying to write, you're defining what the inputs should be and what the bad inputs should be. And so the key is to make those errors explicit rather than implicit. When they're implicit, they're bugs. When they're explicit, your program works correctly. Even if it's like doing a very simple thing, like I'm just going to quit and tell the user you had an error. That's way better than just having an unexpected behavior later in the program. Okay, any other questions on the basics of calling syscalls? So the exciting part here is we're actually calling in to the operating system kernel. We're using this, we're piercing the hardware protection that prevents you from actually, as a programmer, issuing instructions that will touch the hard drive. And we're calling in to the lowest level software in the system that will actually interact with the hardware. And if you know these syscalls, you know the kernel. It's like a kernel, it's like a library, just like standard I/O is a library. And you have kind of the full power that the kernel provides you over the hardware. All right, so today I'd like to go over the rest of the basic file operations. What did I have here? Oh yeah, stat. So I'm going to go over getting metadata about the file. So the file system, along with the content, stores some metadata. And there's actually a bash or a core utility called stat. What did I call this? And this will give you information about the file, like its name, how many hard links it has, its inode number, and timestamps. So in like digital forensics, these timestamps can sometimes actually be useful for investigations. If somebody claims they didn't modify a file, but it has a modified timestamp, and you know that that timestamp was not manipulated, then you can kind of prove something about what happened on that system. Like say somebody claimed some data wasn't tampered, but some files were modified. You could also trick people into thinking they were modified by modifying this. So you as the user, if you have read and write access to this file, you can change these. So for instance, the touch command creates a file, but it also updates the timestamp for a file that's already created. So here you can see that what's changed. All of them changed except birth. So birth is when the file was supposedly created, and the rest are, just when it was accessed, that is open for reading, when it was modified, open for writing, and when it was actually changed, stuff was written to it. So the touch command will update all those. But you could also do it in the past. You could touch and put an old, I forget how to do this with touch, date. Yeah, so I can pretend that this was written maybe I shouldn't show you this, but let's see. I don't know what the format is. I think it tries to interpret it. So let's try to make it the beginning of the epoch. So there we go. Now it claims that it was accessed however many years ago that was, 55 years ago. I don't know if you can change the birth date. I think you might be able to, actually. Yeah, I think you can. Yeah, you can change. Yeah, you can change other times as well. But anyway, so that data is stored with the file in the file system as well. So remember, the directory just stores a mapping from names to inode numbers. This data is stored on the inode number. So if I have a hard link to this file. But anyway, so we're not going to use this. Yeah, go ahead.
You can only kind of change or write to the file. But if you can change the date, only if you have read and write access, right? Yeah,
that's right. Only if you have read and write access. Yeah. Okay, so we're only going to use stat for limited stuff in this class. There's this is all the documentation for it. So there's a syscall called stat. So this is where if you're in the wrong section, if we're in section 1, this is going to be the command line utility. If we're in section 2, this is the system syscall. And the documentation for this is a little spread out. So there's a struct that is the return value of this command. So you see you have to so this is a kind of classic C style programming when you want to return something other than a primitive type. If you want to return a struct, one way to do it is to pass a reference to an already created struct. So this is the library writer saying, I'm not going to create memory, you create memory for me and give me access to it. Has anyone ever seen this pattern? Like struct pass by reference? Okay, not too many people, but common pattern in C. This is the struct you get from the system. So notice the name is not here because the name is part of the directory. It's not part of the file itself. But we have all the stuff we saw in that stat command: inode number, file type, hard links, etc. And there's one flag I'm going to ask you to use for your upcoming project. And I give you the code for doing this, but this is kind of documented deep inside the man pages in this section 7, which is like miscellaneous. But it actually tells you this field of the stat buffer. It's called SD mode, and it'll tell you what kind of file it is. It'll tell you whether it's a directory file or a regular file or some other kinds of files that are available on the file system. So a lot of these other files are not. So notice we have socket here. That's for network programming. This is illustrating the file abstraction. The regular files may be on disk, but these other kinds of and directories, but these other kind of files may not be on disk. They may be other I/O peripherals connected to your device. But anyway, I just want to give the man pages for this so you can have it handy. But I'll give you, mostly give you the things you need to check in that stat buffer. Okay, so here's some example code. Let's see. Here's our stat example. I'm just going to copy it if I can. Oh, God. Let's take a look at what this program does. It's just like our files program. It reads in a path as a command line argument. And then it calls this stat system call, passing in a buffer, a struct. Remember, this is just the definition of the stat sys call. It populates this structure for you. This is the structure that it populates for you. And then I just have some code to print out some stuff from that. This is basically rewriting the stat command. So here's the number of links. Everyone remember what hard links are? What's a hard link in the Unix world? Yeah. Well, not quite. Even if you delete a hard link, the file will still exist. But it's related to that. So hard links are when you have multiple directory entries for the same file, for the same inode number. So the system will actually keep track of how many hard links you have in the file. So it'll use that. Once the last one's deleted, if there's only one link left, then it'll instruct the file system to actually delete the file instead of just removing the link. Or actually, I think the kernel will do this for you. We have the size of the file in blocks, not in bytes. You'd have to convert, and then the type of file. And just a quick overview. I'll give you like most of this code, but this is another common C programming style, especially at the kernel level. This mode field, which holds our file type, it's let's see, what type does it have? So it has a mode T type. So these are all just like bit vectors, where you have one bit representing one value. And so instead of having to remember the number of the bit that is holding that value, you mask it. You use who's familiar with this operation, this ampersand in C? Bitwise operations. Okay. Did you learn this in like CS1, CS2? They taught. Okay. So yeah, you just use bitwise operations to pull out one value from the bit mask. You probably saw this in computer architecture as well, when you have like flag registers. Maybe not. And so this documentation that I showed you here of the modes, these are the bit masks that will pull out the values from this mode. But anyway, this is like really low level kind of bit twiddling stuff. Here's a convention for using it. We use a bit mask to pull out that value, and then we can do a switch statement or an if statement to check the value, check which value it is. So this is the part of the bit, the bits that has the format, what they call format or file type, and these are the actual values that it can hold. So anyway, I don't want to belabor that too much. So let's give it a file. So here I gave it the files.c file. It has one link, has this particular size, and it's a regular file. I could give the current directory as a file, because remember, directories are files. It says there are two links. Size is 4096. That's in like block size. And it's a directory file. So why are there two links for the dot folder? Yeah. Yeah, exactly right. Exactly right. So we've got so very good. We have itself, and then it's also here. I'm back in the parent. It's also here in the parent. So two directories have this file. All right, good. That's directory file. Let's see if we can find some non-regular or non-directory files. So if we go in, so this is a file that will read and write to my physical RAM, and it's a character file. So you can read and write streams of individual characters to it. If we get a disk file, what are disk files called nowadays? Let's look at the video. Also character. Oh, NVMe, that's what it's called. Also character device. Okay, so there's a block device. So these are my hard drive partitions. They're block devices, so that's what file systems expect. Most file systems expect to be built on. Anyway, so this is kind of low-level operating system stuff. Not going to quiz you too much on this. But questions about the stat command? So this is like low-level information about the files on your file system. I'll only have you use this in limited senses, like to test whether something's a directory or test whether something's a file. All right, so let's get to reading and writing files. Thought I'd put write in here. Oh, maybe it's in the... So these are the file operations you'll need for the project. Open, which we went over already, read and write. Here are their man pages, and here's reading in the Linux programming interface, which shows example code, talks more in detail about these calls. But the call names are very simple. It's just read and write. And we can take a look at their interfaces in the man page. So unlike fread and fwrite, there's not a lot of help given to you here. And when the kernel says it's the kernel might fail, the kernel could only give you part of the read that you asked for. And so there's a lot of manual effort you have to do in order to make sure just having 10 bytes gets written correctly. So this gets pretty tedious. We get into the weeds of the kernel interface and really what the behavior is, but it's also a good lesson in the reading specifications, because the kernel gives you a very low-level specification, and if we want to be able to use it correctly, then we need to be able to understand that specification and write code around it to get around the error conditions that the kernel may throw at us. So here's what read does. It attempts to read up to count bytes from the file descriptor. So where does this file descriptor come from? How can we get a file descriptor? What's that? Open. Yeah, so remember the open syscall, that's what gives us a file descriptor. And I hope you're doing the reading of the Linux programming interface. So it'll talk about the process and what these file descriptors are. The kernel just maintains for each process a list of open files that it has. Each one is given a number. This is called the file descriptor. It's just an integer enumerating in a table the list of open files that you have. So this is the difference between the file on disk versus an open file that can be read and write from a process. But so when you call open, you get this file descriptor, which is specific to your current process. You pass that as well as a buffer. So who knows what a buffer is? Who's used buffers? I hope you had to use buffers in CS1, no? Did you have to do string operations in CS1? Okay, so strings are done with character arrays, right? So buffers are just arrays of bytes. And they're used to hold binary data when you want to read and write binary data. And just like in managing strings, you need to allocate memory yourself. So this function, unlike in something like Python, is not just going to read an arbitrary amount for you until it's done reading. You have to tell it exactly how many bytes you want to read, and you have to give it an already allocated array to store that data. So if this array is too short, you're going to run into problems, you're going to run into buffer overflows. If this file descriptor doesn't exist, you're going to run into issues. To make that worse, read only attempts to read count bytes. The kernel can just say, okay, I gave you half the bytes, and then I had to stop and do something else. So you asked for 10 bytes. I gave you 5. And so now you as the programmer have to deal with that particular case. It's not going to happen often if you're reading small amounts of bytes. You'll probably never encounter it. But strictly speaking, you need to handle this. You can't just call read and then you're done. You have to call read, check for an error, check how many bytes you got, and then call read again over and over and over. But okay, let me build up to that. Let's just start with a simple read of a file. So here is all right, so I'm just going to copy the code. I think it's here already. Yeah, read is here already. All right, so here's the code. We open the file. We create a buffer. We allocate memory ourselves to hold the data that we're reading. And then we call the read command. The read command will return how many bytes was given to us by the system. The error is indicated with -1. And so it says here, it is not an error if this number is smaller than the number of bytes requested. So it says this may happen if fewer bytes are actually available. So it could happen if you're close to the end of the file. Maybe there's only 5 bytes in the file, but you asked for 10. Or because it was interrupted. So you'll see this everywhere in the documentation because the kernel allows for asynchronous events. Your syscall might just be, given up on by the kernel. This is called the user losering problem or something like that. If you read that worse is better essay that I pointed out last time, it'll go into that. This is one of the disagreements in system design decades ago about forcing the user of the kernel to have to deal with this error checking. And there are other ways to do this, but this won out because it was simpler to implement, most likely. And so we have this interface everywhere now. Probably most of your phones, like all your phones probably have it. But this is why if you take an operating system class, you design a system in layers. So this may be the layer that you have to deal with in the kernel, but you just build another layer on top of it. That layer is the C standard library. So when you use fread or fwrite, that handles all of this complexity for you. But in this class, I'm just going to have you actually try this, once in your computing career to actually see what it's like to actually program the kernel. Okay, so let's do a simple read. I'm not going to do any kind of error handling here. I'm just going to, not any checking for whether it gave me fewer bytes. But here I've initialized a buffer here, and I've asked it to read 10 bytes and put it into this buffer. And then here I'm just looping over that buffer, however many, up to bytes. So if buff size is 10, what's going to be the value of bytes when I run this program? Any guesses what it might be at runtime? So I asked for 10 bytes. I pass 10 bytes to the read. And if it doesn't error out, how many bytes, what's the return value going to be? 10 bytes? No. So it might be 10 bytes. But remember that the system will only attempt to read 10 bytes. And in its output, it returns the number of bytes it actually successfully read. So it's not an error if this number is smaller than the number of bytes requested. It may actually only read fewer bytes than you asked for. So let me show an example of this. If the file is only 5 bytes long, the kernel is not going to read 10 bytes. It's only going to read 5 bytes up to the end of the file. And you as the developer will know when that happened because the return value won't be 10 bytes anymore. It'll be 5 bytes. So all right, let me show an example of this. Let me show an example of this happening. Oops, just need to, it's a long. Okay, so here's our files. And let me start by reading in. All right, so I read in files.c. Let me show you files.c. Actually, this is files.c. I read in this source code. And I asked to read the first 10 bytes of this file, because when I open it, the pointer in the file is at the beginning. And so indeed, I got 10 bytes as output. Here it said, yes, you read 10 bytes. The kernel told us we read 10 bytes. And here were the bytes that we read. Where is this from? Where in the files.c is this from? Yeah. Yeah, it's the header. It's at the very top. So this is the first 10 bytes of the file that we read in. Now, if I had a file that was only 5 bytes, so here's my TXT file. I think it's 5 bytes because it's got a new line. There's a new line character that echo puts, so it's 6 bytes. Sorry, 6 bytes. My counting is bad. And let's see what happens when we read this. So here, we told the kernel to read 10 bytes, but it returned to us that it only read 6 bytes. And so this is important because you might have garbage data in your buffer, and if you go to print it out or use it, you need to know how many bytes was actually read from the kernel. Okay, so that's the read command or read syscall. Questions about using read? Yeah. In the buffer? Yeah. Yeah. So I could just change this to read buff size instead. Okay. It's just an int. Yeah, so I can force it to print out whatever was in my buffer. And it looks like there's nothing printable in here. So we can't see it being printed out because it's not ASCII characters in that garbage data. But this command od will print out the raw bytes of an input. The -c flag will represent it with C escape codes like /n. So we can see here's the contents of our output, bytes, :space, 6, new line, hello, new line, and then here's buff size, 10. And then here is the 10 bytes that we printed from the buffer. So these only 6 were actually given by the kernel. That buffer that we allocated up here will have garbage values that have values that aren't expected to be read. We can see here we read 10 bytes, so 1, 2, 3, 4, 5, 6, and then 7, 8, 9, 10. Actually, there's an R character in here. So we're in somewhere in the memory space of our program that has this extra data in here somehow. I don't know why or where it came from. Maybe it was from a prior function call. But yeah, this is the extra 4 bytes inside of our buffer. And we don't have to just stop it at 10 bytes. We could read past the end of the array as well. So here's 10 bytes past what the compiler thinks is the limits of our buffer. So this is the source of the classic stack smashing or buffer overflow or overread attacks, where you inspect other parts of memory by reading past an array. But yeah, anyway, good question. Questions on this? So you don't have to worry about this too much. If you're worried about like security exploits, you'll have to understand this at some point. But any questions on the read system call? Okay, let's take a look at write. So writing has the same problem as reading, where the kernel can just say, oops, I made the same mistake. The kernel can just say, I'm going to try to write as much as you asked me to write, but I might fail, or I might get interrupted, or I might not write all of those bytes. So same problem here with read. The number of bytes written might be less than count. Insufficient space, interrupted by a single handler. So strictly speaking, and a lot of C coders probably don't do this if they're using system calls, but strictly speaking, you need to account for that when writing your program. All right, let me do this example. All right, so I have the complicated version here. Let me start with the simple version. Okay, let me go through this program. So we read in 3 arguments this time, or 2 arguments, I should say. We read in a path to a file to write and a string to write to that file. We open it as before, except this time we open it for writing, and we ask the system to create the file, and we also ask the system to zero out the file for us, to basically delete the file for us. And this is the permissions that we're going to set if the system creates the file. So this, I've just given you this. You can use this for the project. Take a look at the man page if you want to learn more about these arguments. And here is all we have to do to do a write. So we've got the number of bytes we want to write. I use string line for that. And we don't need this for now. I'll just comment this out. And then we ask the system, given the file descriptor, to write whatever's in this buffer, the MSG buffer, and try to write MSG count number of bytes. All right, so let's take a file that doesn't exist. So New file doesn't exist. Let's try to write to new file. Hello world. All right, you don't see anything happening, so none of these errors were caught. Let's take a look at new file. You can see now it has hello world in it. So that's just a basic right. Questions on this? Questions on why this happened, how this happened? Yeah.
So you overwrote what was previously filed.
Well, the file didn't exist yet, so the create flag was used for that. But yeah, let's see what happens when we play with these other flags here. So let's say we only open for writing. I'm going to rebuild this. So let's make a file called non-exist, let's make a file called non-exist. So it doesn't exist right now. And let's see what happens when I try to write to this. So open fails because I took out that create flag. So the create flag, the system will not try to, it'll try to open a file that exists, doesn't exist, so it won't create it. Now I could open, say, a file that does exist, like this new file, and write to it. And what do you think new file will look like after I've written to it? It exists already. What'll happen to new file? So before it had hello world in it, and I just put a long string of garbage data, what'll happen to it? Yeah, it got overwritten. So it got overwritten with the contents that I overwrote it with. Let's see what happens when we overwrite it again, but just with a smaller message. So I'm going to overwrite new file again, but I'm going to overwrite it with hello space space space. Let's do hello underscores. All right, so what do you think will happen here? So the file originally had this garbage data in it that that had this content in it, and now I'm overwriting it I wrote hello with underscores to it. What'll the file look like now? All right, let's take a look. So notice it's hello underscores, but all the rest of the content after that is still there in the file. So why? Because that's what we asked the system to do. We said open the file. He opened it. It has all these bytes in it already. We're at the beginning of it, and we just asked to write however many bytes that was. That like 9 or 10 bytes. But the file is 20 bytes, 30 bytes. So it wrote those 10 bytes for us and then stopped. This is what the truncate flag does. When you put the truncate flag, it tells the system when I open it for writing, zero it out, delete all the contents of this. So it's a very minor change, but it has a big effect on your system. So if you're writing systems code, you can easily blow away data. And if you don't try to recover this data could be lost kind of permanently. But notice that when I make this change, now when I ask it to truncate, and I write, I'll just put trunk here. So that's definitely shorter than the file that I have. Now what will be in new file? Just trunk. It'll just be trunk. And all of that other data is zeroed out. So truncate means shrink the size of a file. By default, it means shrink it to 0, which means delete the data. And then we already talked about the create flag. If I go to write a file that doesn't exist, then open will fail. So new2 doesn't exist. And this create flag that will add the option to create the file if it doesn't exist already. So now new2 exists, and it contains the bytes that I asked to write to. Questions on that? Yeah.
You said the write only. How can you also read the file?
Oh, good question. There's another flag that is write and readable. So you can do read write. You can read and write to it.
But you're reading in this case.
No, I'm writing.
Well, when you use cat,
Oh, CAT is reading. That's right. But CAT is after my program ran. So I ran my program, which only opened for writing, and then I ran CAT. So CAT inside of CAT, or at least in the C library that it calls, it's calling open, read only probably, and then calling file read, and then writing it out to the standard out.
oh, so you can't access the function of the file inside the code as it is right now.
As it is right now, no, you wouldn't be able to read. So we could try. Let's see what happens when we try to read from this file descriptor. Let's just read like this. I don't know what will happen. It should fail, I guess. Whoops. Let's do it down here. So let's see what happens when we call read on this. Oh, I didn't check for the error. So I have to double check that that's the exit code. Yeah, -1 is an error code. So let me check. So it just silently failed. And here, so read says bad file descriptor, so it won't let me read from it. But if I had done, what was it? Then it will let me read. Although I'm not printing out the data, but it's reading from it without error. But okay, good question. All right, other questions on reading? Yeah.
So when you write, for example, without the trunk and create class, and you're writing something smaller than whatever is inside, can you write, does it always start writing from the beginning, or can you write from a certain point?
You can write, you can write from a certain point. So this is called, oops, what is this called? Oh, lseek. So there's just like fseek did you guys learn about fseek to move around in a file? So there's a syscall so what the process stores what files you have open and also what position in that file that you're currently reading or writing to. That if you call a read or call a write, it'll start at that position and then move however many bytes the kernel was able to. But you can change that position with this system call. So this will change the position in the file that you're reading from. So you could open it and then say seek 10 bytes ahead, go to 10 bytes ahead, and then read from there instead. So this gives you like ultra precise control over the files on your file system. Other questions on reading and writing? So I know that's super exciting that you have to do this at a low level. I've also put code in here for how to deal with when the kernel fails to give you all the bytes that you asked for besides the end of the file. You basically have to write a loop that will keep trying write until you get everything written out or until there's an error. So I'll let you look at that, but I want to go over the file system project, which is assigned today and due in a couple of weeks. So what you'll do is you'll implement a version of the copy command using the open, read, and write syscalls and stat that we use today. So it's not going to work exactly like copy, but more or less it's going to work like copy. I've also given some bonus project ideas in here where you can extend the copy command. So here's the usage. You'll take the path to a source file, the path to a target file. So the source file should exist and be a regular file. How can we check whether it exists and is a regular file? How can we check whether it's a regular file based on what we saw today? Stat, yeah, exactly right. So we can use stat to check if it's a regular file, and if it doesn't exist, stat will fail. And target file is either existing or non-existing, but in an existing directory. So how can we use the open command to open such a file where it may exist or may not exist, and we want it to be created if it doesn't exist? How can we open for copying that file? Yeah, ocreate and otrunk, because we want to overwrite the file if it exists. So if we don't use truncate, it won't overwrite all of it if the original file is smaller. Questions on that? Questions on the command? So you're just implementing copy, what copy does under the hood. And so I've given you details on input validation. So you'll notice in a lot of the systems programming, the code for like error handling is like 10 times the size of the code for the actually writing. So you could write in kind of unsafe, non-handled version of this in just a few lines of code. But if you want to have all the error handling and make sure it doesn't break the way your colleague was asking about, we need to do input validation. And my tests will actually test these as well. We'll test that your input is being validated the way it's supposed to be. So I've listed these here. Take a look at these. Let me know if you have questions at EdSTEM or next time. And I've given you a specific error code for each of these cases. So if it doesn't have the right number of arguments, the source files doesn't exist, etc., then I've given you exit codes for these. Okay, so the output shouldn't be anything printed out if it's output, but if there are no errors, then the destination file should be a different file. That is, it's not a hard link, and it has the exact same contents as the source file. If the destination file exists, it should be overwritten. If it doesn't exist, it should be created. No need to create any directories. If there's a destination file in a directory that doesn't exist, no need to create it, but you can do those for bonus projects. So copy has features for doing all sorts of other variations of this. I've given you a reference to all the syscalls you're going to need for this, as well as where they are in the man pages, readings in the book. To help you with this, I've given you example code in the lectures for writing this. It must have a make file. So this is how we're going to be building and running it on the grading for the automated grading. So just look at the Hello project. You can just basically cut and paste this, but change the names. And you'll have your make file. It should you can name the source code whatever you want, but the output program should be called myCP for copy. That's the only way we're going to build and run this. So emailing my code to me or having the wrong file name, no make file, it's all going to get like no points because we're going to grade this automatically. And this is the standard practice in any code development. If you go on GitHub and you want to download a command line application, this is how you're going to run it. So I hope everyone with Hello and Git can now submit the projects via Git. We'll get Git graded soon, so I had a little hold up in grading the Git project. But hopefully everyone is good with Git. So I've just given you the local and remote repositories to use for this. Use the Git exercise to review it. Use the instructions in the Hello project for checking that you've had it submitted. And then I've given you test cases. So you can follow these instructions to unpack the test cases and run them. This is how you can run them for a little explanation. And I've given you a detailed table of 13 test cases that you're going to be graded on. Now, to make this more fair for people who turn stuff in on time, only half of these test cases will ever be released. The other half will never be released, but they're described here. So I figure that's the compromise. I always had trouble with public and private test cases. It never really works out. And it also is like, if you just turn it in late, it kind of gives you a benefit if you just turn it in late. So I've given you detailed instructions for what the test will test for, but I've only given you the scripts for half of them. So the odd number ones you have downloadable and you can run. The even number ones, just make tests yourself and make sure it works. And remember, you can always resubmit, so you can submit past the deadline. You can resubmit past the dedeadline as often as you'd like till the end of the semester. So if you get things wrong and it doesn't pass the way you expect, you can always resubmit and be regraded for a very, very small penalty, 0.5 points out of 8 points. So for the projects, I have very lenient policy because I want everyone to get the projects done and not be so worried about the deadline. Yeah.
Is it like 0.5 points per day?
No, it's just 0.5 points ever. Yeah. So I can't have no penalty because then the incentives are wrong. But I don't want too much penalty because I want you to actually get it right. Because otherwise, if you have too much penalty, then even if you fix it, you won't overcome the penalty. But in this case, you're likely to get a better grade. And with the bonus points from attendance and bonus projects, you can get more than you lose on the late projects. So that's my kind of what I think is a cool design of the class, so that it incentivizes you to do the stuff and not just like cheat your way through or argue your way through, but also has some, like realistic penalties. So you actually have to do the work. All right, here's the grading scheme. Git repo exists. Program is written, builds, and runs as described here. So if these two things don't work, none of the test cases will work because we're automatically grading based on pulling from the Git repo. If you didn't get Git right, you're going to get a 0. If your make file isn't right and it doesn't run, you're going to get 1 point. So you can easily tell what error happened. It's kind of like an error code, actually. And then for the 13 cases, we're just going to prorate it across 6 points. All right, questions in our last couple of minutes? Yeah. No. So if it passes 13, you get 6. So I couldn't figure out how to. Is this not clear? Prorated. So proportional to the number of test cases that pass. So unfortunately, I have 13 of them. So if you where's my calculator? So if you get 10 out of 13 of them, you'll get this many points, 4.62 points. Make sense? So unfortunately, there's 13. I usually try to make them an even number because of my obsession with even numbers. But this time, yeah, they're all like point. This is how many points there are per test case, basically. But a lot of them are very simple. So it's like there's 3 for argument checking. And a lot of them are different variations of stuff. So remember, half of them are available. The odd ones are available. The even ones will never be available. That's my approach. So I think this will work. I hope this works this semester. I've always never had the right way to have public and private test cases. I think this will work. I hope. All right, other questions in our final minute? All right, so there's the next project. And have a good week, everyone.